The weights are no longer frozen. The weights in every frontier model you use today are mathematically static the moment pre-training ends. Google Research's latest work on nested learning aims to change this by reframing the model not as a fixed graph, but as a hierarchy of optimizers that update at different speeds. Instead of a single training phase followed by frozen inference, this approach treats every forward pass as a potential weight update. The paper, titled The Illusion of Deep Learning Architectures, argues that the distinction between a model's architecture and its optimizer is actually an arbitrary one. By nesting optimization loops, researchers have found a way to let models absorb new facts into their core parameters without the catastrophic forgetting that usually destroys fine-tuned systems. This shift moves us away from static checkpoints toward the mechanics of the Hope architecture. Optimization is an architectural primitive. In the nested learning framework, common optimizers like Atom or SGD are redefined as associative memory modules. Think of it like this. Your current transformer uses a fixed attention mechanism to find patterns, but a nested learning system treats that mechanism as a mini-optimizer that learns the context on the fly. Google's researchers demonstrated that backpropagation itself can be written as a single-step gradient update within a larger nested sequence. This allows the model to compress what it sees into its own weights at multiple timescales. While a standard LLM has one global learning rate, a nested model has fast updating inner loops for immediate context and slow updating outer loops for long-term knowledge. This multi-level approach is what allows the Hope architecture to manage its memory density. The Hope Architecture and CMS. The practical implementation of this theory is the Hope architecture, which builds on the earlier Titans memory modules released by Google. Hope uses what is called a continuum memory system to bridge the gap between short-term context and long-term parameter storage. The mechanism works by gating new information based on surprise. If the model encounters data that contradicts its internal state, it triggers a weight update in a specific nested layer. This avoids the high compute cost of full-scale retraining because the updates are localized to the relevant optimization loop. However, the engineering trade-off is significant. Implementing nested loops increases the complexity of the gradient flow, making these models harder to stabilize during the initial pre-training phase compared to a standard transformer. This balance between stability and plasticity is the core challenge for the next iteration of the continuum memory system. The shift to perpetual refinement. The transition to nested learning marks the end of the frozen model era by turning weights into a dynamic data structure. By collapsing the optimizer into the architecture, as seen in the Hope and Titans papers, we move from a world of version checkpoints to models that perform perpetual refinement. For developers, this means the end of RAG as a mere retrieval patch, and the beginning of models that actually internalize private datasets as they process them. The two-tier system of training versus inference is merging into a single, continuous process of context compression. While the compute overhead for managing these nested loops remains high, the benchmarks show that models with multi-frequency updates retain 40% more niche knowledge than standard fine-tunes over long durations. The signal to watch now is how Google integrates these continuum memory blocks into the next release of the Gemma weights later this year. Subscribe for more